All right, practice simple pendulum. It's a fairly straightforward one. It's a good example of using ratios to solve a problem. So before I put the problem up, kind of a quick reminder, when we were solving this stuff for the simple pendulum, we had, oops, that would be a theta, and since this part is our omega squared, that means omega is the square root of g over L, and we'll be making use of 2 pi over the period is the square root of g over L in order to do this. So let's have a look at the problem. It's going to be this one, a pendulum with a period of 1.5 seconds on Earth, writing that down, is taken to Mars, where the gravitational acceleration is about 0.3 times that of Earth. And of course, on Earth it's going to be 9.8 meters per second squared, or 9.81, somewhere in that range. What will the period be on Mars? Okay, so first I'm going to rearrange this equation. Oops. T is equal to 2 pi square root of L over g. Now what I'm going to do is write the period on Mars divided by the period on Earth, write a ratio of the two. That way I don't need to go through and figure out the length because it's the same pendulum, I've just taken it to a new location. Let me see, so for Mars we'll have 2 pi square root of L over g Mars. On the bottom we'll have 2 pi square root of L over just g on the Earth, the 9.8 meters per second squared. Okay, and of course you notice we get a huge amount of cancellation when we do that, resulting in the square root of g on the Earth divided by g on Mars. So this is going to be over relatively quickly here. It's not a terribly challenging problem. You could also use t on Earth, figure out what the length would have to have been on Earth, and then use that to solve the problem. It works just as well, but as you can see, it does take a lot longer to do. So 1.5 seconds on Earth. I'm going to leave that as g because we know the bottom is 0.3 times g. So that means we're really just doing 1.5 seconds times the square root of 1 over 0.3. Okay, so times square root 1 divided by 0.3. And we get a time of 2.74 seconds on Mars. It does seem like a bit of a silly question, but hey, you actually happen to have things on you sometimes that have a fixed length. For instance, you happen to have a necklace. Well, a necklace has a particular length to it, and most of its weight tends to be on some little decorative thing down on the bottom, or at least sometimes it is. And that could be used as a pendulum, and you could potentially use that to figure out the gravitational acceleration wherever you are by measuring the period on Earth or knowing what it was and then taking it somewhere else. Okay, used to know of an anime series where it was a plot point that the main character had a necklace that would swing once per second. It was a very weird thing. And yes, I am an enormous nerd. Alright, that's actually it for this example problem though. So when you see problems related to simple pendulums, you're going to see things that are a bit like this, where you're relating period, length, and g. You could be figuring any of those out. I will point out one thing which may be interesting for future assignments. G can become an effective G. And cases where that might be interesting is, imagine you are inside of an elevator that's undergoing acceleration, and you have your pendulum sitting inside of it. In a case like that, the effective force that's acting on it, you'll basically end up with tension minus mg equals ma, so your tension will become kind of effectively this mg plus a, where the g plus a would be your effective g. So yeah, if you're in an elevator and it's continuously accelerating upwards, you're going to see a period that's a bit shorter because you effectively have a larger gravitational acceleration. If it's actually accelerating downward, you'd see a slightly smaller effective g, which means, much like on Mars, you'd see a longer period. Alright, that's going to be it for this example problem. I will see you in the next video. As soon as this wakes up and lets me stop recording. Hello. There we go.